Hi guys, thanks for joining. I'm just trying to wait to see if we've got some stragglers on the way. Given that I had to change the link for live, at the last minute because I'd done it wrong. So sorry about that. Just to make sure that you're in the right place, this is the 0625 IGCSE Physics session. We'll cover core and extended on really the habits as opposed to individual parts of the content to work on today. And then there will be some time at the end for you to ask any questions or if you have any particular questions that you want to go through. So let's just take a quick look at how many people we've got. This is my first ever YouTube live, so sorry if it's a little bit clunky. I haven't done this before. Yes, there will be some question solving in the stream. I would, just before we get started, if I were you, I would have your calculator, pen, pencil, paper in front of you, just so that you can try and work along with us. And yeah, let's begin. Okay, so the 4 habits that I really want to talk about today, I'm really leading with technique here. So one of the things I've spent a lot of time in the last few weeks, especially really reading through all the examiner reports and just upskilling really on what exactly is. I mean, I obviously have a lot of experience from my own students, what kind of things they repeatedly drop marks on. But I wanted to look at what that looked like across the whole cohort for the last 15 series, so back to 2021. And these are really the main things that have come up. So I really want to make sure that you guys are aware of, you can spot them and not make the same mistake. So one of those is covering the options first. We will obviously go into more on each of these as we go through the presentation. But really what that means is don't just look at what the options are and then try to make one of them work. Okay. What we want to be doing is trying to figure out the answer to the question. Really ignore the 4 options initially. Try and work it out as you would if it was on the theory paper, let's say. And then when you have what you think is your final answer, if that matches one of the A, B, C, D, you're going to be a lot more confident with that, rather than what I've seen in the past where some people try to sort of reverse engineer the answer and start from whatever answer A is. They'll try and plug that into an equation and see if they can get back to some other value. Sometimes that might be, if you're really panicking and you don't have a clue, you might want to try and reverse engineer and try it that way. Maybe you'll get somewhere. But again, I wouldn't be really looking at doing that as your main approach. That's if you've got 5 minutes left and you're trying to fill in the couple that you haven't managed to solve on the way through. Okay, so let's look more at that one. So work on the physics before you read A to D. Therefore, the wrong answers aren't going to get in your head and sort of sway what you're thinking about. Okay. The fallback on this, which I'll discuss the question that we're about to get into, is if you're stuck, if you can eliminate 2 of them, which you often can, very unlikely that you're going to then have a selection out of 4. You should be able to eliminate 2 of them, and then of course you've only got a 50-50, so an educated guess, if you like, rather than just just a complete guess. So this is the first one we're starting with. Parallel resistors. This question comes up quite a lot. And yeah, so I'll just give you a little bit of time to have a look at that one. What I'll say is, obviously, we are working to about a mark a minute on this test. So I'm just going to give you a minute now to have a look at this first. Try not to look at A, B, C, D before you start, right? Now, you'll notice with this one, you haven't actually got numbers, okay? So it seems like a strange one to say, okay, how am I going to try and work this one out without looking at the answers when there's no numbers available? Now, of course, you're always, from the information given, it says two resistors with resistances R1 and R2 connected in parallel. Resistance of R1 is greater than the resistance of R2. Now, it doesn't give you any numbers, but of course, we could make up the numbers, right? We could say, okay, we're going to call R1 2 and R2 1, let's say. Or R1 is going to be 10, R2 is going to be 5. Okay. And then you can put those numbers in, actually work it out if you know the equation for the total resistance of a parallel combination, which will come up on the screen in a moment if you don't already. And then you can work it out. And once you have a value, then you can just see which one, A, B, C, or D, fits the value you got. That could be your approach. Okay, I can see someone in the chat says they don't understand the question. We are going to go through this one in a moment. Right, so that's about your minute up. So how would we actually go about this one then? Well, if you already know the content really well, then maybe straight away you know the answer, okay? That's great if that's the case. But if you don't, then we need to look at how are we going to narrow this down, okay? So let's have a look what we're going to start with. If we have R1 and R2 in parallel, then of course the overall combination is that likely to be equal to either R1 or R2? Is that possible? I'm just looking in the chat to see people's responses. I am seeing quite a lot of you saying that you're going to go for A. So it is A. Our total has to be smaller than the smallest of the resistors that are in parallel. Okay. Now, that's something that if you know the content well enough, hopefully you already knew. Okay. Let's say that that wasn't something that was already ingrained in here, though, right? Because we know that the parallel combination is 1 over R total, is equal to 1 over R1 plus 1 over R2. Now, of course, we know that once we add those together, we're going to have to do the reciprocal. That's another mistake that people often make. But what happens here is because we've got an extra branch for the current to go down, let's say we only had R1 here, and then we add in an extra branch with R2, there's no situation ever where that does not decrease the overall resistance, because what we're doing is we're giving an extra path for the current travel. Okay. If we give it an extra path, we've still got the original path, which has the same resistance as it did before. So the same amount of current will be drawn from the cell that goes down that path. Add in another path, in this case R2, means that even if that's a huge resistor, there's still going to be a tiny bit more current flowing because you've got that extra branch. So what that means is you always end up with the resistance of a parallel combination being less than any of the resistance on any of the branches. Okay, so that's the answer. But how could we have narrowed it down better if we didn't know that straight away? Okay, well, because we know how this equation works, 1 over R1 R2, and then we're going to do the reciprocal once we've done that, it cannot possibly be equal to R1 or equal to R2 because we've got a parallel combination. That's not possible. So B and C we could eliminate straight away. Now the other one, the average of R1 and R2, that is the trap here. Okay, that's the one that a lot of people, without really thinking, just go, oh well, it's probably the average, and you just go with that one straight away, right? So imagine that you had 6 and 8, let's say. R1 is 8 ohms, R2 is 6 ohms. You add them together, half it, 7 ohms. Okay, crash box. No, that's not correct because of the way that the parallel combinations work. 1 over 8 plus 1 over 6, add those together, do the reciprocal. You'll notice that that does not give you 7. So that's a trap that is quite widely used. Never go, oh, it's going to be the average. The other thing to note, just while we're on this, if you are given a parallel combination and it says the resistors are identical, then what happens then when you put it into this equation is that you end up with, if there's two of them in parallel, then the total resistance is half, which also makes sense because you have two identical branches for the current to travel down. Okay, so the resistance overall is half. Same thing, if there's three all in parallel, then the overall resistance would be a third. Okay, so this is what the examiner report said. It says most candidates thought that the total resistance of two resistors in parallel is equal to the average of the two resistances rather than it being smaller than either resistor. There is also a good analogy, which is called the bathtub analogy, which you might want to look up if anything I just said to do with increasing the current as you add more branches in parallel. If that didn't make total sense to you, then look up the resistors bathtub analogy for parallel combination. Okay, as I said, D is the tempting one. It says average. B and C, we should know that is not possible if you know the equation. And yeah, just remember, parallel is always going to be less than any of the individual branches. Okay, second one. This one comes up a lot as well. If it's momentum, if it's forces, any vector additions, and you need to make sure you are consistent with your step. Okay? You need to make sure that if it says that something is moving to the right and then bounces off and ends up moving to the left, you can't possibly say that the velocity was, let's say, 10 before and now it's 8. No, if it's going in the opposite direction, if we're saying that the direction it's traveling in the first place was positive, then when it has bounced off of the other thing, then it must be traveling at negative 8 meters per second, let's say. Okay, so I would always, just with a little note somewhere off to the side of the question, just draw an arrow and just write plus VE or positive next to it, just to show what direction you are saying is positive. So we're going to try and use that one now and apply that habit to the next question. So a tennis ball with momentum 2.3 kilogram meters per second is struck by a tennis racket. The racket causes the direction of motion of the ball to reverse. The racket exerts an average force of 1,500 newtons during the impact with the ball, and the racket and ball are in contact with each other for a time of 0.0024 seconds. So what is the magnitude of the momentum of the ball as it leaves the tennis racket? Right, 4 options. Again, I would try and avoid looking at those really for now. Have a go at this question. I've got a 1-minute timer on my watch that I will come back to you after that has elapsed. Also, the first question was a core question that could come up on either. This is an extended. I'm trying to sort of jump between the two so that I don't sort of front load it as core and then do extended later. I'm just going to go through as we go and sort of jump between the two. Bit of something for everyone. Before we go through this one, actually, one thing I forgot to mention, this last question, the first one, this was actually on all 3 of the variants from that year. So the November 2021 paper 1s, this was on all 3 variants, and this same comment was made about the mistake that was made, and D being the most most chosen trap, if you like, or distractor. Yeah, so that is really important, because if it's coming up on all three papers in the same series and they're making the same mistakes across the board, that means it's not a localized problem. Oh, in this region they didn't teach that very well or didn't understand that very well. It is one of the real major things that people misunderstand. Okay, I think I've given you long enough now for the momentum one. So let's have a look. Now, if we were trying to follow what we said before, we're going to set a positive direction first. Okay, so let's say that we are saying that the direction of the tennis ball initially is the positive direction. So we're going to say initial direction is positive. That means it has positive 2.3 kilogram meters per second of momentum traveling, let's say, to the right, if you were going to draw it as a little diagram. Now, we're given that the average force is 1500 newtons and that it is in contact with the ball for 0.0024 seconds. So we can work out the impulse, which is F delta T. So 1500 times 0.0024 gives us 3.6 kilogram meters per second. Okay. But we have to also think, all right, that force was actually in the opposite direction to the momentum, right? The momentum was going to the right. The force must be acting to the left, because the ball's going to ping off to the left in a moment after this force has been applied. So that's where we've got this extra step here. Or you could have put the minus in there with the 1500. So we've got the impulse is minus 3.6 kilogram meters per second. Okay. As long as we're then really clear on our direction. Now, we also know that impulse is equal to the change in momentum. So we've got 2.3, positive 2.3 kilogram meters per second, plus minus 3.6 kilogram meters per second, leaving us with 1.3 kilogram meters per second as our final answer. Now, that is the magnitude is 1.3. Of course, it is actually minus 1.3 with our sign convention, but it only asks for the magnitude. And that is where some people will get mixed up, because they'll accidentally, maybe straight away, as soon as they get to 3.6 kilogram meters per second, they just go, okay, it's B, because they've already looked at the values and they've seen, oh, well, I've got to one of the numbers. Okay, that must be right. That is the trap here, by not sort of completing the calculation that you're doing. You've seen, oh, that number's shown up. Okay, that must be the right answer. Big one there. People not actually getting to the final answer, whereas they probably would on a theory paper, because they'd have in their mind, okay, I'm trying to get to the magnitude of the ball after the magnitude of the momentum of the ball after the force. Then, of course, you're going to work all the way to get there. This is where, like I say, if you've already looked at the answers or potential answers, and then you see that you get to one of them, it can be real tempting to think, oh, I must have done it. I've got one of those. And then you don't complete the sum. You don't get to the value that is actually being asked. If it had asked for the change in momentum, then of course, great. That would be B. But we do need to make sure we get all the way to the end. So the most common incorrect answer for weak candidates was option B. They only calculated the change in momentum. And some other candidates did choose option C because they didn't consider the direction of the ball reverse. Now, if you think, where did that one come from? Well, that 3.6 kilogram meters per second as the change in, and this is again where choosing our direction really comes in handy, because 3.6 plus the initial 2.3 would give you 5.9. But again, that is not correct. That would suggest that somehow it's sped up, okay, even though it's actually changed direction, okay. That, yeah, it's definitely not C. It's definitely not B. D, I'm not even sure where D came from in terms of the options. But yeah, A must be the correct answer. Right, B is the input on its own. C adds the magnitudes and ignores that sign here being really important. If you do 2.3 plus 3.6, you're going to come out with the wrong answer. And you've done everything right at that point. So that would be a real shame. Okay, on to habit 3. This one is core and extended. And of course, the previous one, the choosing the direction, I've done a extended question for it, but of course, you do have to also do that in core. Now, converting to SI units before you do any substitutions. Okay, this happens so often. You really need to make sure you're really on top of this, right? This is going to be on multiple of the questions, obviously out of 40. This could drop you 3 or 4 marks easily in the test if you are not on top of it. Now, personally, I tell my students to just learn the prefixes, and I would not even bother doing the divide by 1,000, let's say, to go from milliamps to amps. Personally, whatever the value is, I just tell my students to write the value into their calculator, hit the times 10 to the button, the standard form button, and just put -3 if it's milli. Just put times 10 to the 3 if it's kilo, times 10 to the 6 if it's mega. If you learn the prefixes, you don't need to worry too much about, oh, do I divide or times by 1,000 on this one? All that kind of thing. If you just remember what the prefix actually means, as in the K here, killer, just means times 10 to the 3. So you can just write the number. Let's say it's 1,000 kilowatts, 1,000, then hit your times 10 to the and put 3 on your calculator, press equals. It will already then display in watts. Okay. So that would be my advice on that one. Obviously, remembering that there's 60 seconds in a minute. We know that there's 60 minutes in an hour. There's 24 hours in a day. You can really work through that one. Now, of course, you can remember that, okay, if 60 times 60 is 3,600. You can remember that, but you don't need to. You can obviously just use your calculator and do steps at that point if you need to. Now, the other one that is really common is seeing any area or volume measurements and having to convert those. People make the mistake of not realizing that we have to do this conversion in all of the dimensions that we're talking about. So if we're just talking meters to centimeters, then of course it's a scale factor of 100 just in one direction, length measurement. Okay. If you have an area, you have meters squared. So you have a meter in this direction, you have a meter in that direction. That means that you have 100 centimeters in one direction and 100 centimeters in the other. So how you actually have to look at that is you multiply by the multiplier. So let's say that we're going from meters to centimeters. We know that we must multiply by 100 to get how many centimeters a meter is. So if we have centimeters squared, then we will do multiplied by 100 squared. Okay, so 10 so times 10 to the 2 in brackets, and then put the squared on the outside. If you know your laws of indices, you therefore know that in this case, with it being cubed, centimeters to meters is divided by 100. Centimeters cubed to meters cubed would be divided by 100 to the power of 3, or 10 to the minus 2 to the power of 3, which will give you your 10 to the minus 6. Okay, so let's jump into this one. This one actually does look at 2 conversions in the same question, so just be careful on that one. That's why it's extended. Exactly the same kind of questions do come up in core. This one's just a little bit of a challenging one, which I wanted to throw at you just to challenge you in case something like this comes up in a few days' time. All right, have you had long enough there? Anyone need another 30 seconds? Okay, so if we want to change this into SI units before we really get into the question, what are we going to do? Well, we're going to first of all look at this one. We're going to look at 830 milliamps and either do that times 10 to the minus 3. So 830 times 10 to the minus 3, it equals, you'll show 0.830 in your calculator. Or we can just divide by 1,000, which again gives us that same value. And I would make a note of that before you even do anything else. Okay. Especially, I mean, of course, you've already done your written theory paper now, but especially showing you're working in this way going forward, especially if you go on to study A level, it is a huge, huge, huge differentiator. The people that show they're working in the right way all the time, because it just gets you into the habit of making sure that you're not missing out a little in bits of information and therefore dropping marks that are unnecessary. So converting first, we get 0.830 amps. We then are going to plug into Q equals IT, or a rearrangement of Q equals IT. We obviously want the time, so we'll rearrange so that we get T is Q over I. We know that we have 18,000 coulombs, and then divided by 0.830, because of course current is just charge flow per second. So that's why this equation is the one that we're going to use. So 18,000 divided by 0.830 gives you 21,700 seconds, roughly. Then if we divide that by 3,600 or by 60 and then 60 again, that will give you about 6 hours. So that one should be D. All right. The examiner report on this one says the most common incorrect answer is option B, suggesting that candidates had a power of 10 error when converting milliamps to amps. And then they are error when converting time as well. Okay. So just being consistent, making sure that you do that conversion before you get into anything. That could become a real nightmare if, let's say, you do 18,000 divided by 830, then you divide by 60, then you divide by 60, and then you're a bit like, oh, wait, where am I here? Like, I've not taken into account the milliamp. And then it can be a lot trickier, especially if it's something that you're not used to try and make that conversion at the end. Much better to get everything into SI units before doing anything, and then you will, you'll just be consistent throughout and hopefully get to the right answer. Did we all get D there? Most of you did, it seems. I see someone in the chat is mentioning that you didn't memorize the formula yet. Let me just throw the chat for you. This might really help you for your definitions as well as formulas. Oops, that was all. Oh, that's the A level one. My apologies. Let me just go. Sorry, this is the GCSE one. Sorry about that. Dropped the wrong one. There you go. Sorry. All right. So if you check that one out, that's got the formulas and definitions, and it's kind of like a little drill for you to practice them. That might be helpful for you. All right. So moving swiftly on. This one is something that I actually already sort of hinted upon with, I think it was the momentum question before. So finish every step. This again, all of these things do sort of feed into each other, all of these habits that I'm trying to distill in you. So if we don't finish the last step, of course, that is going to mean that you don't get to a final answer that is the correct final answer. Okay. So this one is, well, the question is going to be on a background count. That's the first example that it mentions here. So background count is a big one for this. Pressure is often a pressure difference rather than just what is the pressure. Um, yeah, with decay, making sure you count all the half-lives, with changing momentum, making sure that you have actually worked out whatever it's asked for, whether it is the final momentum or the initial momentum, anything like that. Don't just work out the change in and not add it or take it away. That kind of thing. See it so often, and of course, the distractors that they put in that are the wrong answers, they are going to be ones that students naturally gravitate towards because it's making a specific mistake or missing out a step or not quite getting to the next step. So they always make sure the distractors are other answers that you might end up with on your calculator. That's why we need to, in a lot of ways, just ignore the options initially, get to a final answer just like you would if theory test, and then if the answer is there, fantastic, you're more confident with it. If it isn't, you know you've done something wrong and you need to have another look. Now, like I said before, I wouldn't use, oh, I'm going to try and plug in what I've been given as a potential right answers. I'm going to try and do that and rework it and go backwards to see if I can get to the numbers that I was given in the question. Like I said, could work at an absolute last result, but it's going to take you a while because you're going to be trying it 4 different times, most likely. I would just, if you're confident with the formulas and the physics, work it out on your own and then see if it matches one of the steps. All right, let's jump into it. Okay, so background count in 3 steps. It says a detector placed near a radioactive isotope gives a measured count rate of 800 counts per minute. The half-life of the isotope is 3 hours. So the background count rate is 32 counts per minute, and then it wants you to tell what is the count rate on the detector after 6 hours. All right, so 1 minute for that one. On the same wavelength. All right, I can see a couple of you have got answers in the chat. If the rest of you want to just have a stab and let me know what you think. All right, it does seem like most of you are getting the same answer from the chat. So let's have a look. Let's see. Okay, so what are we going to do here? Let me just go back 1 second. It says here, background count. Subtract it, work the physics, then add it back. So let's make sure that we follow those rules. Okay. Now, background count rate is 32 counts per minute. That means that that count rate must have been included in this measured count rate. So first thing we're going to do, 800 minus the 32 to get the actual count rate that's from the isotope. So that would be 768 counts per minute. What we then look at is what's going to happen over the course of 6 hours. Now we know the half-life is 3 hours, so let's think about that as half 3 hours, one half-life, another 3 hours gets us 6 hours, so 2 half-lives. Now we just said that we had 768 as our counts per minute. We're going to divide that by 2 and then by 2 again. Okay, so that gets us to 192 counts per minute. So you can see why, if you'd already read the options, at that point you might have gone, oh, sweet, A. And then again, you've fallen straight into the trap that they've set for you. Okay, so that is the point where we need to make sure we're going to add back in that 32 counts per minute. So 192 plus our 32 is going to give us 224. And thankfully, that is the option that the chat were just saying. Now it says here, examiner report, weaker candidates realised that they had to subtract the background count rate from the initial reading on the detector, but forgot to add the background reading back on at the end and therefore chose option A. That is, you would not believe how common that is. Possibly the most common trap of all of these. So really, really, really common. You just need to be really aware of it. Make sure that you think about it at the start. Is the count rate that you've been told, is that including background? Is that already minus from background? Make sure that you're really clear on that. And then whether you need to add that back in at the end if you are trying to say what the detector would be reading. Okay, so subtract and halve, but forgetting that last step is a really common thing. Like I said, it can happen on any type of question, really, where you get so far, it's a multi-step calculation. You get so far, you see that you've got to one of the answers, and you just circle it. And unfortunately, then you have fallen straight into the trap that they've set for you. All right, so those are the 4 things that I really wanted to focus in on. Obviously, it's only a very short session, 45 minutes this morning, afternoon, evening, wherever you are. So they're the things that I really want you to be clear on. Those technique changes will just help you to spot any small little traps that they're setting for you. And yeah, if you're able to make sure that you're consistent with those things, then that should help you no end in obviously scoring as well as possible. Yeah, so I did want to then open it up to some of your questions. So if you want to drop any of those in the chat, I have got maybe another 5 or so minutes. I'm running an A-level one of these almost directly after. So I haven't got loads of time, but yeah, any questions that you've been struggling on, I do have all of the papers here, but it might take me a second just to find the right one. But if I look at the one that's been mentioned there, so May, June 25, 22. Let me have a quick look for that, and I can share it on my screen, hopefully. Question 17. Okay, let me just. Sorry, just taking a moment here because I'm not very used to using the live stream, but I'll be with you in a moment. right, so June 25, paper 22. Sorry, no, yeah, question 17, that was. Okay, so the top one on that one. So it says, hopefully you can see that okay, folks. Yeah, I've just, rather than snipping it and put it into the presentation, just opened the PDF, so it might be a little bit small, but which wave will diffract the most when passing through a gap that is 0.85 meters wide? So for that one, you just need to understand this is really mainly a content question. If you know it, you know it. If you don't, then it's going to be a little bit tricky. This is knowing that in terms of diffraction, the maximum diffraction you're going to get, the maximum spreading as waves go through a gap, is when the wavelength of the wave matches the size of the gap. Okay, if you're given the wave speed and you're given the wave frequency, we know that v equals f lambda, so we can work out lambda, the wavelength, by doing v over f. And if you work out v over f for each of them, whichever one is closest to 0.85 is going to be your winner. Answer C kept getting D. Let's have a look. I'll just check the math scheme that I've got to see whether that matches what I have. 22. Yep, answer is C. Yeah, so if you do each of them, you're going to do 300 over 280 is 1.07. 300 over 400, 0.85. 350 over 280, 1.25. 350 over 400 is 0.875. Oh, yeah. Yeah, you're right on that one. I mean, technically, I sort of see where they're coming from on it. I would expect that for that one, that they would be looking at you understanding that being closest to having the same wavelength as the gap. That's a condition for good diffraction. Now, going a bit further than that, what you then learn at A level, or I usually teach at A level, is that when we're saying that, we're talking about the order of magnitude. If we have a magnitude for the wavelength that is really different to the gap size, then of course you're not going to get much diffraction. Okay, as in if the wavelength is much smaller than the gap, then it's just going to go through. It's like walking through some double doors. We don't have to squeeze through that or anything. We just walk through because you're much smaller than the gap. So then there's not really going to be much diffraction. What happens if you are of the same sort of order of magnitude? Then at that point, the larger the wavelength, the bigger the difference is going to be. So yeah, I would have probably actually got that one wrong myself, thinking that they were wanting you to go for the one that's closest. Yeah, so that's another little trick that they're obviously playing. Any others that anyone wants me to look at quickly before we round off? All right, I can jump back to looking at any others if you find one in the meantime. Let me just round off the presentation though. So obviously, making sure that we are covering the options, don't get swayed by the options that are there. You don't want them to be changing what you would do. You want to just figure out the answer fully, then see if one of the options is actually um, matching what you've worked out. Making sure that anything that is a vector, you are in a positive direction. So you're saying, okay, to the right is positive. That means that straight away, if you know anything is moving to the left, sign. Or even if it comes out in the maths that you get a negative, you're like, oh, that must go in the opposite direction. Um, it might work out like that, that rather than you being given the situation and having to think about the minus, it might come out in the maths that you're like, oh, actually that means this. Making sure that you convert into SI units. I gave you a couple of little hints or tips on how to do that as easily as possible. Just because I noticed that people sometimes make mistakes and accidentally multiply by 1,000 when they should have divided by 1,000, that kind of thing. So just using the prefix and putting it directly in your calculator as times 10 to the minus 3, let's say for milli, or times 10 to the 3 for kilo, can be really helpful. So you're making those small mistakes, and then making sure that we are getting all the way to a final answer before you go and circle whichever option you're going for. If you do all of those things, that should save you dropping silly marks. I've tried really to work on technique here as opposed to just, oh, this bit of content, this can be this bit. If you do enough past paper questions, you will see all of the types of questions that come up. The things that are going to keep tripping you up are going to be technique based. Obviously, you want to make sure that you're not repeating the same mistakes over and over again over time. So, obviously, you've already seen my website and what I've been putting together. CIEinsider.com. You can get the replay and any other live sessions going forward. For you guys, I imagine that some of you, this will be the end of your physics journey, which is absolutely fine. Obviously, you've got to pursue whatever is right for you. Anyone that is continuing on to A or physics next year, there will be yeah, I'm here to help. So I don't know exactly what it's going to look like, but I am going to be putting on something next year to help students through both the GCSE and what might be relevant to you guys A level. So I'll send out a couple of emails about that. One other thing that I haven't mentioned but meant to is that there is also going to be a little free gift for having attended today. I put this together really from, like I said, looking at all the examiner reports and really looking into and analysing what trends there are sort of across the world for these papers. So I'll send you my deep dive analysis on that as a sort of thank you for attending. There's also a one-page version, so you'll get an email about that after this session. If you didn't register for the session, if you didn't register for the session and get the emails, then you can jump into that now. I'll just post you the link so you can, if you haven't already and you want to register so that you get the free guide, the breakdown of all of the sort of traps and distractors that come up over and over again. Just register now, even though it's after the session. That will all work good, and you will get the email with the link to the resource. All right, so let me just have a quick look in the chat. May, June 23, variant 1. Let's have a quick look. I might have time for one, maybe two more. So, May, June 23. Sorry for that one. May June 03 variant 1 question 7, was that on the extended paper? Was it paper 2? Paper 21, yeah, okay. Okay, question 7, did you say? All right, let me just try and host that. Sorry about this, just taking taking a little bit of time to find the right one. So 23, paper 21. I found it myself. It's just to actually show it on the screen for you guys is a little bit finicky. But question 7, that one at the top there. All right, so if that's the right question, if you can just confirm it, yeah. So it says train is traveling horizontally in a straight line. A book is on a table in the train. The diagram shows all the forces acting on the book. Right, so we've got the contact force, we've got the weight, we've got a frictional force. This is how is the train moving? Okay, interesting. So acceleration to the left of the diagram, acceleration to the right of the diagram, uniform speed to the left of the diagram, or move at uniform speed to the right of the diagram. Okay, so how are we doing this one, folks? How are we thinking about it? If you could put in the chat what you're thinking, then I will try and give you some pointers if you're thinking is slightly off. I'll just give everyone the chance to actually have a look at it. Obviously, whoever suggested it has already seen it, but if everyone else wants to just have a look and suggest what you think. Okay, so yeah, that would be the most common wrong answer, I would say. So initially thinking that the frictional force would oppose the motion, so I thought it would go to the left, but apparently not. You're absolutely right. It is a common misconception that that would be the case, and that is because we're looking at a different type of friction here. We're talking about static friction, which is actually holding the book in place and is actually accelerating the book in the direction of the movement of the train. Okay, so if it was dynamic friction and there was friction on the book, then of course that friction is opposing the motion. It always is going to. Any drag force has got to oppose the motion. It's also why it increases with greater speed, especially in the example of air resistance. But let's think about this. If there is no frictional force on this book, then when the train accelerates, the book slides off the table. Okay, so if the book is going to stay in place on this table, then there must be enough static friction that the acceleration of the train means that the book is going to be held in place by friction, which is essentially going to accelerate the book relative to the ground, let's say. It's not going to accelerate the book relative to the train. It's going to stay in position on the train, just like if you were stood up on the train, your feet being in contact with the train helps the train's momentum to also transfer momentum to yourself, and you end up moving in the same direction of the train. Okay, so that's the thing to really think about. Is this object actually moving relative to the train? No. Okay. And the only reason it's not is because the frictional force is holding onto the book and accelerating that book with the train. If it didn't have, let's say that somehow this was an ice carriage and the book was sat on a table made of ice, then when it starts to accelerate, there wouldn't be enough frictional force, so the book would slide and it would essentially not accelerate in step with the train, and it would slide backwards. Okay. How do we determine whether it's accelerating or at uniform speed? If it was at uniform speed, there wouldn't be a frictional force because once it's moving at that speed, it is just, there's no forces acting horizontally on the book anymore. Otherwise, it would be accelerating forwards or backwards. All right, last one then. Someone said question 30 in the same paper. Ooh, I like this one. AC generator. Okay, so AC generators. Graph shows the potential difference between points X and Y plotted against time. A positive value of PD indicates that X is more positive than Y. Okay. Again, I'll give you a moment to have a look at that one. All right, so what it's actually asking us is which diagram shows the position of the coil at point P on the graph. Okay, so that is when we are at maximum negative PD. Straight away, actually, when we talked earlier about trying to get rid of options so that if you are going to guess, it's going to be an educated guess, which two straight away could this not be? Someone just said that they're the same drawing for A and C. They're not, but I can see why you'd say that. If you see where the wire loop is connected, the slip rings, on the A1, Y is connected to the left-hand side of the loop. On the C1, Y is connected to the right-hand side of the loop. So yes, correct. It can't be B or D because at B and D, that is where the PD is going to be 0 because spinning through, let's say, a degree of an angle of 1 degree at that point doesn't come through any field lines. Hence, that's at that point is 0. Okay, so then it's just working out: is it A or is it C? Okay. Now, in this case, we need to think. Okay. So as I say, a positive value of PD indicates that X is more positive than Y. That means that if we are looking at this spinning, then we are, and also it's a generator, not a motor. So you need to think about the right-hand rule. That means if we look, if you align your hand north to south, your first finger, second finger being current, and then the direction of how it's spinning means that your thumb is going to be upwards, and we're looking at the left-hand side, if you like, of that coil. As that spins upwards, that is going to cause a current to go clockwise around this loop, and is going to give you C as your answer. Okay, so it must be connected that way around because this is spin clockwise. Therefore, if we look at that, means that the left-hand part of the loop, that wire is moving upwards, the right-hand side is moving downwards, and so then if you use your right-hand rule, you should see that it comes out as being C. And yes, good point. Yeah, the crux of this, for PD to current must flow from X to Y, if we transform Y to X, PD would be negative. Very, very good point. Yeah, so it's just working out which direction or in which of these orientations that is going to be true. Okay, folks, I have stayed on a bit longer than initially planned, but I do need to jump off to prepare for the A-level one of these. So I hope that's been somewhat helpful. Please do follow along and let me know. Do reply to the email that I sent out if you are going to be continuing on to AS next year, because yeah, I'm going to keep trying to put things out there to help those of you that are doing that. If anyone is not, and this is the end of your physics journey for now, I do get lots of people telling me how they didn't love physics in school, but now they do, like, you know, when they're more of an adult. So maybe you'll come back around. But yeah, good luck for your exam. And yeah, I hope it goes well and that this has been helpful. Take care.